Water and wastewater can be treated in many ways. Today, we will be focusing on the removal of disinfection byproducts. But first, let's look at what disinfection is. Disinfection is a method to selectively kill organisms and pathogens such as viruses and bacteria in water and wastewater. Whilst the sterilization of all microorganisms is preferable, it is not necessary in disinfection. There are many forms of disinfection processes used around the world, including the likes of mechanical, physical, chemical, and UV treatments. For the purpose of understanding the removal of byproducts, we will be focusing on the use of chemicals such as chlorine and chloramine disinfectants because they are the most widely used globally. More specifically, we will look into how chlorine reacts with microorganisms to produce byproducts, the health effects caused, removal of the byproducts, and regulations set for safe drinking water.
Disinfection byproducts, as discussed, are chemical, organic and inorganic substances that form during a reaction when organic matter, which is the decay of vegetable and animal matter, that are present in the water come in contact with the disinfectant such as chlorine. Seen in the table, there are numerous disinfectants that are used such as chlorine, underchlorine acid, chlorine dioxide, chloramines, ozone and many more. All of these disinfectants produce various organ-halogenic disinfectant byproducts, inorganic disinfection byproducts, and non-halogenic disinfection byproducts. I will be addressing the most common disinfectant used, which is chlorine. The types of byproducts produced due to chlorine can be observed in each of these categories. Organ-halogenic disinfectant byproducts include trihalomethanes, haloacetic acids, haloacetonitriles, chlorine hydrates, chloroprysin, chlorophenols, N-chloramines, halofuranose, bromohydrins. Inorganic disinfectant byproducts include chlorate, and non-halogenic disinfection byproducts include aldehydes, alkanic acids, benzene, and carboxylic acids. The process of using this disinfectant is called chlorination, and it's when the chlorine reacts with naturally occurring organic matter, producing a complex mixture of byproducts, especially of halogenated compounds, which are the organic byproducts. Trihalomethanes, known as THM, and haloacetic acids, known as HAAs, are the primary byproducts found in high concentrations. There are many more byproducts which are produced, however, due to their generally low concentrations of about less than 0.01 milligrams per litre and often less than 0.001 milligrams per litre. The main byproducts will be addressed in more detail in regards to what they are, the chemistry behind it, the effects it has onto the water, in addition, important health effects associated with these particular byproducts. The first byproduct to be looked at, found in chlorinated water, is trihalomethanes, or THM. Having its chemical compound being CHX3, this byproduct can be divided up into trihalomethane, bromine dichloromethane, chlorine dibromemethane, and tribromemethane. These substances are formed during the reaction between the organic matter in the water and chlorine. The byproduct's concentration is usually higher when bromine are present in the water, higher pH value of the water, and seasonal weather, especially during summer due to the increase in temperature, which increases the organic matter content in the water, thus increasing the concentration of THM. THM concentrations have also been known to exceed groundwater concentrations due to the types of organic matter in the water. The chemistry of this reaction is complex and not fully understood, but the chemical reaction can be observed in the following two equations. The suspected health problems associated with THM include damage to the liver, kidney, and central nervous system. It is also known that they are considered carcinogenic, which is why reducing this byproduct while not compromising the disinfection is important. Haloacetic acids, known as HAAs, are the second type of byproducts which are important in chlorinated disinfection byproducts. This byproduct is found in higher concentrations than THM. It is through the biological decomposition of HAAs that THM are formed. The concentration of this byproduct is determined by the pH value of the water. When the pH value is lower, more HAAs are formed. The amount of HAA formed is due to the composition of naturally present organic matter, also like THM. During summer, concentrations in surface water exceed concentrations in comparison to winter. Acetic acids consist of 3 hydrogen atoms, which are fixed to a COOH group, where the hydrogen atom are replaced by halogen atoms. This can be observed from the chemical reaction seen. The health effects associated with haloacetic acids are suspected to raise the risk of cancer, similar to THM.
In the management of DBPs, there are 3 possible strategies, these being 1. Controlling disinfection process to minimize DBP formation. This may be achieved by selection of optimal disinfectant dose or strict management of the disinfection method. 2. Removal of DBPs after disinfection. 3. Removal of DBP precursors from untreated water prior to disinfection. This is the most active strategy and works by minimizing the formation of all DBPs rather than targeting a specific set. The second strategy will be outlined in detail in this presentation, with the removal process of the 3 most common DBPs formed during disinfection by chlorination being discussed. The combination of the use of activated carbon and biodegradation as a water treatment process is known as biologically activated carbon filtration. This filtration process works by 2 distinct mechanisms which synergize together to remove DBPs. The interaction between different aspects of this process is represented by the diagram presented. Firstly, activated carbon has a high surface area and highly developed pore structure. As such, it has high absorption rates, allowing contaminants and dissolved oxygen in the water to be absorbed onto the carbon structure. In the same way, microorganisms are able to be accumulated on the surface of the activated carbon under optimal temperature and nutrition conditions, meaning haloacetic acid degrading and trihalomethane degrading bacteria are able to reproduce on the surface using the dissolved oxygen from the water. Secondly, the bacteria biodegrades the DBPs through an enzymatic process called co-metabolism, or by using the byproducts as a sole carbon and energy source. For THMs, this degradation is achieved by ammonia oxidizing bacteria. However, the byproducts can be toxic to AOBs, and as such, both the THM and the THM removing bacteria are consumed during this process. This is the process of co-metabolism. For HAAs, this degradation may be achieved by several different bacteria, which aerobically degrade HAAs co-metabically or as a sole carbon and energy source. As this degradation occurs, it promotes the regeneration of the activated carbon so that more absorption is possible after being fully saturated. While chlorine analogues such as chlorite and chlorate left over after the disinfection treatment can also be removed by activated carbon, the process of using ferrous ions to remove chlorite from water will also be discussed. The reaction of ferrous ions with chlorite is represented by the following equation. During the process, ferrous ions react with chlorite in the presence of water and is oxidized to form insoluble hydrated iron oxide, chlorine ions and hydroxide ions. As the product of this reaction is insoluble, it is very easily removed by sedimentation and or filtration. It may also be noted that the reaction occurs very fast, being completed in only 3 to 5 seconds at a pH range of 5 to 7, with a pH of 7 being optimal, leading to the highest efficiency of chlorite removal at 99.6%.
The removal of disinfection byproducts may not destroy all the unwanted organisms in the water. As a result, the government has provided regulations on disinfection byproducts to ensure healthy and safe drinking water. As outlined in the Australian Drinking Water Standards 2011, It was found that if trihalomethanes in water exceeds 1 milligram per litre, it is likely to pose a significant risk of health issues in humans. As a result, the regulation against the presence of this byproduct is 0.25 milligrams per litre in Australia. The Australian Drinking Water Standards does not provide specific guidelines for haloacetic acids. However, there are regulations for its most common compounds. Chloroacetic acid is regulated at 0.15 milligrams per litre. Dichloroacetic acid is regulated at 0.1 milligrams per litre, and trichloroacetic acid is regulated at 0.1 milligrams per litre. Additionally, while the Australian standards do not have guidelines for chloride, the World Health Organization stipulates that the maximum amount of chloride that can be present in water is 0.7 milligrams per litre. The formation of disinfection byproducts is inevitable in water treatment when using chlorines as disinfectant. Vigilant monitoring and strict adherence to guidelines regarding safe levels of these byproducts is essential to both the known and unknown health effects posed by ingestion of these chemicals. While the removal of DBPs via the means of biologically activated carbon filtration and ferrous iron treatment after they are formed is effective in reducing levels to a tolerable region for ingestion. Additional employment of strategies which minimize their initial formation, these being control of disinfection process to minimize DBP formation, removal of DBP precursors from untreated water prior to disinfection, offer a much more efficient, dynamic, and active approach to effective management of DBPs in water treatment.